Welcome back, everyone, to another deep dive. This time we're diving headfirst into the world of magnetism.
Sounds electrifying.
Well, magnetic, haha. But seriously, we're cracking open a physics textbook today.
Ooh, textbook time, getting into the nitty-gritty.
Yep. Specifically, we're looking at a chapter on magnetism and matter.
A classic.
We want to go beyond the basics, like how magnets stick to your fridge. We're going to unravel some of the deeper mysteries behind this force.
I think a lot of people take magnetism for granted. I mean, think about it. It's everywhere, like compasses.
Yeah. And even bigger, the Earth's magnetic field. It literally protects us from solar winds.
Right. It's incredible how this invisible force shapes our world. But when you really get into how it works, it gets mind-bendingly fascinating.
So let's start with something I think we all know, the bar magnet. You've got your North Pole and your South Pole.
The classic duo.
But here's a question that's always bugged me. Why can't you have just one pole? Like, can you ever chop a magnet in half and end up with just a north or just a south?
Ah, the quest for the magnetic monopole. It's a question that has fascinated scientists for centuries.
And have they found it?
Well, the answer, at least based on everything we know so far, is a big fat no.
So no matter how many times you split a magnet, you'll always end up with a north and south pole.
Yep, always a pair. It's like they're destined to be together.
There's got to be some law of the universe preventing those magnetic monopoles from existing.
You're thinking like a physicist. And you're on the right track. It comes down to magnetic field lines.
Okay, those I remember. But remind me.
These invisible lines of force always form closed loops, and that's a key difference from electric field lines, which, unlike magnetic field lines, can actually start and end at charges.
So because magnetic field lines always loop around, you always have to have both a north and south pole.
Exactly. It's like a continuous flow, a never-ending magnetic circle, always connecting those two poles.
Okay, I'm starting to see the connection here, but I gotta ask, these magnetic field lines, are they like real? Can we see them?
Great question. We can't see them directly, but we can definitely visualize them.
Oh, how?
Ever seen those cool demonstrations with iron filings and a magnet?
Oh yeah, the filings like make a pattern.
Exactly. The filings arrange themselves along these invisible field lines, revealing the shape and direction of the magnetic field. It's like suddenly seeing the unseen.
That's a super cool way to make those invisible forces visible. But now I'm curious, what's actually going on inside a bar magnet to create these field lines, like at the atomic level?
Well, our trusty textbook actually dives into this. Prepare to have your mind blown. It basically says that a bar magnet is like a collection of tiny atom-sized current loops.
Wait, what? Tiny current loops, like little circuits running inside the magnet?
Yeah, think of it like a city full of tiny electrical circuits all flowing in the same direction. They all contribute to the magnet's overall magnetic field.
So like each atom is like a tiny little electromagnet. Whoa, that is mind-blowing. How do they ever figure that out?
It's amazing what scientists can discover, right? And this idea leads us to an important concept, magnetic dipoles.
Ooh, dipoles. Now, I remember learning about electric dipoles a while back. Is there like a connection here?
You're good at spotting patterns. There are some really striking analogies between electric and magnetic dipoles.
Like what?
Well, both of them experience something called torque, which is a twisting force when you put them in an external field. And their potential energy, it also depends on how they're oriented in that field.
So it's almost like nature is using the same basic design for both, just with a few tweaks.
It's like nature loves symmetry. And speaking of symmetry, the textbook, it actually lays out these similarities really nicely in Table 5.1.
Tables. Oh dear, are we about to get into some serious equations here?
Don't worry, no hardcore math today, but the equations are there if you're curious. Scientists have actually figured out how to calculate the magnetic field around a dipole using, equations. It's pretty cool.
Cool, but my brain prefers pictures, to be honest. Does the textbook have any visuals to help understand all this?
Of course, they wouldn't leave us hanging. There's this great example 5.2, that uses magnetic needles to show how dipoles interact. You can see how they attract or repel depending on how they're facing each other.
So it's like a little magnetic dance.
Yeah, it's a good way to picture the dipole interactions.
All right, dipole interactions, got it. But I'm still stuck on this whole no magnetic monopoles thing. Does that mean there's like a rule book for how magnetic field lines have to behave?
That's a great question, and it brings us to Gauss's law for magnetism.
Gauss's law. Sounds serious.
It's a fundamental principle. Basically, it says that the total magnetic flux through any closed surface is always zero.
Flux. Remind me what that is again?
Imagine, like, drawing an imaginary bubble around a magnetic field. Flux is the amount of magnetic field lines passing through that bubble.
Okay, I'm picturing it. So if the total flux is zero, does that mean, like, for every field line going into the bubble, another one has to come out?
You got it, and that's why magnetic monopoles can't exist. If they did, you could imagine drawing a bubble around just the North Pole, and then you'd have flux going out, but none going in.
So it breaks the law.
Exactly. Gauss's law says, nope, not allowed.
Fascinating. So we've covered bar magnets, their secret inner lives of tiny current loops, those magnetic dipoles, and even a fundamental law of magnetism. I'm feeling pretty magnetically charged up already. But I know there's more to this world, like how do materials themselves become magnetized?
You're ready for the next level. And you're right, it's not just about the permanent magnets we're used to. It turns out different materials respond to magnetic fields in all sorts of ways.
Okay, now I'm really intrigued. Let's dive in. All right, so spill the beans. How do materials become magnetized?
Well, it's not like every material gets magnetized the same way, right? There are different, like, magnetic personalities, you could say.
Magnetic personalities. Okay, now I'm really curious.
The textbook actually breaks it down into three main types. We've got diamagnetic, paramagnetic, and ferromagnetic.
3 types. Okay, that's a lot to unpack. Maybe we should tackle them one by one.
Sounds like a plan. Let's start with diamagnetism. These guys are kind of the introverts of the magnetic world.
Introverts, what do you mean?
They're actually repelled by magnetic fields.
Repelled, like they don't want anything to do with magnets.
Pretty much. Think of it like this. They see a magnet and they're like, nope, not interested.
So they're not just not attracted, they actively push away.
Exactly.
Huh, I never knew that was even possible. What kind of materials do that?
Well, it turns out diamagnetism is actually present in all substances to some degree.
Really? Everything?
Yep. But it's usually so weak we don't even notice it. The textbook mentions bismuth, copper, and even water.
So even water's a little bit diamagnetic. That's wild. I mean, why would something be repelled by a magnet? Doesn't everything have at least a little bit of iron in it?
Well, it all comes down to the electrons in the atoms. Those little guys are constantly orbiting the nucleus, right? And as they orbit, they create tiny, tiny current loops.
So it's like every atom is its own mini electrical circuit.
Kind of. And when you apply a magnetic field, you're basically messing with those current loops. It induces a current that opposes the field.
Oppose it. So it's like the electrons are fighting back against the magnet.
Yeah, you could think of it that way. They're trying to cancel out the magnetic influence. And that leads to a slight decrease in the magnetic field inside the material, and that's what causes the repulsion.
Okay, so diamagnetism is all about those electron currents pushing back against the magnet. That makes sense. But I'm still trying to wrap my head around the fact that it happens everywhere, even in water.
I know, it's pretty mind-blowing. But here's something even weirder. Have you ever heard of superconductors?
Superconductors. Yeah, Vega. Isn't that something to do with electricity?
It is, but they also have some pretty crazy magnetic properties. Superconductors, they exhibit what we call perfect diamagnetism.
Perfect diamagnetism. So they repel magnets like 100 times stronger than regular diamagnetic materials.
Not exactly stronger, but they completely expel magnetic field lines. They're like, magnetic field, not in my house.
That's so cool. Like if you put a magnet near a superconductor, would it just float there?
Yep, that's actually a real thing. It's called the Meissner effect, and it looks like magic.
The Meissner effect. I'm adding that to my list of cool science words, but how does that even work?
It gets a bit complicated, and it involves some quantum mechanics, but basically, in a superconductor, the electrons pair up and flow without any resistance.
No resistance. So they're super efficient.
Super efficient, and those flowing electrons, they create these perfect counteracting currents that just kick those magnetic field lines right out.
Wow. Superconductors sound pretty amazing.
They are. They have a ton of potential for all sorts of futuristic tech, like magnetic levitating trains.
Maglev trains. Okay, now I'm definitely seeing the sci-fi potential. All right, so we've got diamagnetism, the introverts pushing back against the magnetic field. What's next on our magnetic personality tour?
Next up, let's talk about the paramagnetic materials. These guys are a bit more social.
Social. How so?
Well, unlike the diamagnetic materials, they're actually attracted to magnetic fields.
Ah, so they're a little friendlier towards those magnets.
Yep, but their response is still pretty weak compared to the superstars of the magnetic world.
Okay, keep me in suspense. What kind of materials are we talking about here?
Think aluminum, sodium, oxygen. Those are all paramagnetic.
So those are attracted to magnets, but not super strongly? What's going on inside them that's different from the diamagnetic materials?
Well, in paramagnetic materials, the individual atoms, they actually have their own permanent magnetic dipole moments.
Wait, so each atom is like a tiny little magnet itself?
Yeah. But the thing is, these moments, they're all jumbled up, pointing in random directions.
So it's like a chaotic magnetic mosh pit.
Perfect analogy. But when you apply a magnetic field, things start to get a bit more organized. The field encourages those magnetic moments to align with it.
So it's like the magnetic field is a conductor trying to get the orchestra in tune.
Exactly. And that alignment leads to a slight increase in the magnetic field inside the material.
So the material becomes a little bit more magnetic because those tiny atomic magnets are starting to line up.
You got it. But here's a fun fact. Temperature plays a big role here.
Oh, how so?
Well, the warmer it gets, the more those magnetic moments want to wiggle around randomly. It makes it harder to get them to line up.
So it's like trying to herd cats.
Exactly. The hotter it gets, the more those cats, magnetic moments, want to do their own thing.
It's hilarious. So to get a strong paramagnetic response, you need a cold temperature and a strong magnetic field.
That's the recipe. Okay, ready for the main event.
Bring on the magnetic superstars. You mentioned them earlier.
Time to talk about the ferromagnetic materials. These are the ones responsible for those strong, permanent magnets we all know and love.
Okay, I'm ready.
So we're talking iron, nickel, cobalt. They're the big players.
What makes them so different? Why are they so much stronger?
The secret lies in something called domains.
Domains. Is that like a magnetic kingdom?
Not quite. Domains are actually tiny regions inside the material. And within each domain, all the atomic magnetic moments are aligned in the same direction.
Wait, so each domain is like a perfectly organized little group of atomic magnets.
Yep, it's like each domain has its own little magnetic army all marching in step. But initially, all these domains, they're pointing in random directions, so there's no overall magnetization. The material as a whole isn't magnetic yet.
Okay, so it's like those little magnetic armies are all scattered around, not really working together.
Exactly. But when you apply an external magnetic field, things start to change.
Oh, well, sounds like things are about to get interesting.
The domains that happen to be aligned with the field, they start to grow. They're like, hey, this field agrees with me, let's expand.
So it's like the magnetic field is picking its favorites.
Kind of, and the domains that aren't aligned, they shrink.
So it's a magnetic turf war.
You could say that, and as more and more domains align with the field, the overall magnetization of the material gets stronger and stronger.
So that's how you get a really strong magnet, by getting all those little domains to line up.
Exactly. But here's another twist. What happens when you remove the external magnetic field? Do those domains just go back to their random ways?
That's a good question. I guess it depends on the material.
You're right. Some ferromagnets, we call them hard ferromagnets, they hold on to their magnetization even after the field is gone.
So they have a good memory.
Exactly. They're like, I remember you, magnetic field, and I'm keeping this alignment. Think permanent magnets, compass needles. Those are made from hard ferromagnetic materials.
That makes sense, but what about the ferromagnets that don't hold on to their magnetization?
Those are called soft ferromagnets. They're a bit more forgetful, you could say.
So they easily lose their magnetization.
Yep. Think soft iron. It's a classic example.
Okay, so we've got hard ferromagnets, the ones with good memories, and soft ferromagnets, the forgetful ones. What determines whether a ferromagnet is hard or soft?
It all comes down to how easily those domains can reorient themselves after the field is gone. In the hard ones, those domains are pretty much stuck in their aligned configuration, but in the soft ones, they can easily rearrange.
So it's like some materials have really stubborn domains and others are more flexible.
A good way to think about it. Now, one last thing about ferromagnetism. Remember how we talked about temperature affecting paramagnetism?
Yeah, the warmer it gets, the harder it is to get those magnetic moments to line up, right?
Well, temperature also plays a big role in ferromagnetism. In fact, if you heat a ferromagnet up high enough, it actually becomes paramagnetic.
Whoa, what? So heating up a magnet can completely change its personality.
It can. At high temperatures, those neatly aligned domains, they start to break down. It's like the heat is shaking things up, causing those magnetic moments to lose their order.
So it goes from a strong, organized magnet to a weaker, more chaotic one.
Exactly. It's pretty amazing, right? So we've covered our three magnetic personalities. Diamagnetic, the introverts, paramagnetic, the followers, and ferromagnetic, the superstars.
Wow, my brain is buzzing with all this magnetic knowledge. I feel like I've leveled up my understanding of magnetism. But is that it? Are those the only three types?
Well, we've covered the basics, but the world of magnetism is vast. The textbook mentions some other, more exotic types of magnetic materials.
Ooh, exotic materials, do tell.
Things like ferromagnetic and antiferromagnetic materials, they have their own unique behaviors and properties, but maybe those are a topic for another deep dive.
Another deep dive. I'm already looking forward to it. Wow, so we've covered a lot of magnetic ground here. From simple bar magnets to those mind-blowing domains inside ferromagnetic materials.
Yeah, and we even explored those magnetic personalities like the introverted diamagnets and those superstars, the ferromagnets. It's pretty amazing how differently materials can behave around magnetic fields.
Absolutely. It's like each material has its own unique way of interacting with those magnetic forces.
It really makes you appreciate the complexity hidden within, like, seemingly simple magnets, right?
For sure. So maybe we should do a quick recap of the key takeaways from our deep dive into magnetism and matter, just to solidify everything we've learned.
Sounds good. Where should we start?
Well, I think a good place to begin is those magnetic field lines, those invisible lines of force that surround a magnet.
Right. And the fact that they always form closed loops. no matter what.
Yeah, which leads to that whole mystery of the magnetic monopoles. We just can't seem to find a magnet with only a north pole or only a south pole. They always come in pairs.
It's like some fundamental law of the universe is saying, nope, no solo poles allowed.
Exactly. It makes you wonder what the universe would be like if we could find those monopoles, though, right? Would it change everything we know about magnetism?
Now, that's a question for the physicists to ponder. But moving on, I think another big takeaway was that, it's not just the permanent magnets we're used to. Materials themselves can actually become magnetized.
Right. We talked about those three magnetic personalities.
Yep, like those diamagnetic materials. They actually get repelled by magnetic fields. They're like, back off, magnet. I need my space.
I love thinking of them that way, like they're putting up these tiny little magnetic force fields to shield themselves.
Pretty cool. And then we have those paramagnetic materials, the ones that are weakly attracted to magnets.
Right. It's all about those magnetic moments inside the material trying to align themselves with the field, like a little bit.
Exactly. It's like they're trying to get organized, but they're not quite there yet. And then, of course, there are those ferromagnetic materials. Those are the superstars of magnetary.
They're the ones that make those super strong magnets we use every day. And it's all thanks to those incredible domains.
Those tiny regions inside the material where all the atomic magnets are lined up perfectly.
It's amazing to think that there's so much complexity happening at such a small scale, like a whole magnetic battle going on inside a single magnet.
Right, and the outcome of that battle determines whether you end up with a hard ferromagnet, like a permanent magnet, or a soft ferromagnet, which loses its magnetization more easily.
It's pretty wild. And to think, all that magnetic knowledge came from just one chapter in a physics textbook.
It's amazing what you can learn when you dive into a topic, right?
Absolutely. And speaking of diving deeper, one thing that really stuck with me was that a ferromagnet can actually become paramagnetic at high enough temperatures.
Oh, yeah, that was fascinating. Like the heat is just too much for those domains to handle, and they start to break down, causing the magnet to lose its strength.
It's a good reminder that temperature can have a huge impact on magnetic behavior. Makes me wonder what other factors might be at play, right? Like, could pressure affect a material's magnetic properties? Impurities?
Those are some great questions, and I think they highlight the fact that even though we've learned a lot about magnetism today, there's still so much more to explore.
So much more to discover. And that's the beauty of science, right? There's always another question to ask, another mystery to unravel.
Exactly. So keep those magnetic moments spinning and never stop exploring.
Well said. I think that's a perfect note to end our magnetic deep dive on. We journeyed from simple bar magnets to the complex world of magnetic domains, exploring how different materials